I now call to order the Society's 2,421st meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Melstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to tonight's lecture by Shep Dolman and colleagues Michael Johnson and Andy Strominger on black hole imaging, being conducted by Zoom from Washington, D.C. and Boston, Massachusetts, and live streamed to the PSW Science YouTube channel. Tonight is the 89th annual Joseph Henry Lecture. We will begin with a few words in his honor, introduce new members, and read the minutes of the 2,420th meeting and the President's lecture by Joachim Frank on cryo-electron microscopy. We will then turn to this evening's lectures, followed by an all-hands-on-deck Q&A session. After the Q&A, we will thank our speakers, make a few closing remarks, and adjourn the meeting. First, please join me in thanking the sponsors of the 2019-2020 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a very generous donor who has asked to remain anonymous. Please also join me in thanking the sponsor of tonight's Joseph Henry Lecture, the intellectual property law firm of Millen, White, Solano, and Brannigan. Tonight's lecture honors Joseph Henry. Henry was the founding president of PSW and served in that role from 1871 until his untimely death 7 years later in 1878. He was the preeminent American physicist of his time. He is now best known for his work on basic aspects of electricity and magnetism, most particularly his work on induction. He was a theoretician and an experimentalist, and he had a practical inventiveness. His finding that magnetic fields are induced by passing an electrical current through an insulated conductor wound around a ferrite core led him to develop strong electromagnets that could be turned on and off at will. This work led directly to the invention of the telegraph and of the telephone. And in fact, Henry developed early versions of the telegraph and consulted with Samuel B. Morse on his work on telegraphy. Henry was very active in science organizations, and he served many important roles in them, including serving as founding secretary of the Smithsonian Institution, as well as first president of PSW. His unexpected and untimely death was headline news not just in the United States, but around the world, and the Capitol shut down entirely to mourn his passing. In his honor tonight, we use the Society's ceremonial gavel. The gavel was carved from timbers originally used to rebuild the White House, after our very good friends, the British, burned it to the ground in the War of 1812. This particular wood was recovered when the White House was completely rebuilt during the Truman administration over a period of years from 1949 to 1952. Of course, we now enjoy a special relationship of a different kind with the UK. Time can turn enemies into friends. And we use this gavel today in the spirit of Joseph Henry's devotion to science, his accomplishments, and the promise of the scientific enterprise to bring about a peaceable and better life for all. I am pleased to announce that the following new members have been elected to the Society. Ben Dubois, an executive with Omelas, interested, sorry about that. Excuse me. Ben Dubois, an executive with Omelas, interested in evolutionary history and astronomy, who comes to PSW through the PSW Meetup Group. Richard Oberman, Chief of Staff, House Committee on Science, Space, and Technology, interested in space and aeronautics, earth science and paleontology, quantum science, and artificial intelligence, who learned of PSW from friends. Camilla Lindstrom, Senior Program Officer at the World Bank, interested in exobiology, animal communication, and the ethical implications of new technology, who learned of PSW from a colleague. And tonight's speakers, Shepard Dolman, Michael Johnson, and Andy Strominger, whose interest will be clear in small part from tonight's lectures. Please join me in welcoming them to membership. New members are entitled to receive a signed reprint of Volume 1 of the PSW Bulletin. If you are a new member and you have not received your copy, please send information telling us where to send it to PSW Corresponding Secretary, Robin Taylor, at correspondingsec@pswscience.org. If you didn't catch the address, it is on the website. We will now turn to the minutes of the last meeting. Our recording secretary, James Heelan, will read the minutes of the 2420th meeting and the President's lecture by Nobel laureate Joachim Frank on cryo-electron microscopy, delivered to the Society on 21 February in the Powell Auditorium of the Cosmos Club. James, the screen is yours.
Thank you, Larry. Good evening, everyone. On February 21st, 2020, at the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the President's Lecture and 2420th meeting of the Society to order at 8:05 p.m. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, Joachim Frank, Professor of Biochemistry and Molecular Biophysics and of Biological Sciences at Columbia University. Frank was co-recipient of the 2017 Nobel Prize in Chemistry. His lecture was titled, Single Particle Cryo-Electron Microscopy, Revolutionary Methods for Determining the Structures of Biological Molecules in Their Native States. To understand how life functions are constituted in a cell, scientists need to understand how molecules within cells interact. Because those interactions are not readily observable, Frank said scientists must examine subsystems in isolation and infer how the whole system functions inside a cell. He then summarized what he termed the ancient history of X-ray crystallography and electron microscopy, or EM. X-ray crystallography exposes crystals to high-intensity X-rays. By observing the diffraction pattern, scientists can determine this crystal's structure. This technique is only useful on highly ordered crystals and is further limited due to crystal packing in sample quantities. EM forms projection images of molecular structures, but because electrons are readily absorbed and damaged molecules, samples must be very thin and electron doses must be low, between 10 and 20 electrons per square angstrom. The results are noisy images. In 1975, Frank developed the concept of a single particle technique by which multitudes of identical single particles would be imaged at the same time to capture the various random orientations. By taking many such images, the molecule could be more quickly reconstructed in 3 dimensions. Frank and others quickly developed Rather, they subsequently developed a formula called the detection equation, by which they determined single particle reconstruction could be applied to molecules embedded in ice. In 1981, Frank and his colleagues used a multivariate statistical analysis to sort images by using computational techniques with quantitative criteria. He credits a program he observed applying such analysis to one-dimensional vectors which coded for blood samples, into which he was able to import his images to produce clustering. Frank explained how he and his collaborators then resolved how to find the angles of reconstruction using random conical tilt. In 1987, using negative stain technique on a 50S ribosomal subunit, Frank achieved the first single particle reconstruction. He subsequently moved his research into cryo-EM, in which a specimen is frozen. Robert Glaser developed the technique with liquid nitrogen, but Glaser's method produced air bubbles that would allow water crystals to form and damage samples. Frank said he decided to use liquid ethane, allowing instantaneous heat transfer that freezes water into vitreous ice and does not damage samples. Frank said this development was revolutionary because it allowed molecules to be embedded in a form close to their natural state. This technique allowed for the first clear ribosome images at moderate resolution. Other scientists determined that applying maximum likelihood methods of classification could extract several structures at the same time from the same sample. Frank said this development allowed scientists to fill the gaps between structures with biochemistry to tell the story of individual molecules. By 2013, Frank said the single particle technique had reached the maximum 5.5 angstrom resolution possible on film. Around that time, the first commercial detectors that could detect single electrons with large signal-to-noise ratio became available. These detectors made the resolution revolution possible, as scientists were able to increase single particle cryo-EM resolution to as much as 1.3 angstroms. Frank then showed and explained ribosome, AMPA brain receptor, ryanodine receptor, and cystic fibrosis ion channel images he has captured using these modern detectors. New technologies include time-resolved cryo-EM, which looks at short-lived states of 10 to 1,000 milliseconds, which require a microfluidic chip to observe. Although the first devices used silicon, Frank is experimenting with organic polymer. Lastly, Frank described mapping a multidimensional continuum of states by compiling millions of images. Using such a continuum, scientists can infer and confirm the existence of short-lived states. Frank then answered questions from the audience. One member asked whether scientists could see molecular energy. Frank answered that, while continuous motion was not observable, scientists are able to see GTP and ATP interactions. Another member asked about the costs of single electron cryo-EM. Frank said the requisite microscope cost approximately $5.5 million, and the camera $600,000, which is why there is no national strategy for centers. As a solution, some scientists advocate using lower voltages, which may result in equivalent or lower resolution images. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:44 p.m., President Milstein adjourned the meeting to the social hour. Temperature, 1 degree C. Weather, clear. Attendance in the Powell Auditorium, 96. And viewing through the live stream on the PSW Science YouTube channel, 28. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. The minutes will be posted to the website. If you have any corrections to the minutes, please send them to the corresponding secretary at correspondingsec@pswscience.org. That's corresponding sec, SEC, at pswscience.org. We now turn to the 89th annual Joseph Henry Lectures on the Event Horizon Telescope and the first images of a black hole. We're very fortunate tonight to have three speakers who have been deeply involved in the study of black holes and in creating the Event Horizon Telescope and taking the first images of a black hole. Shep Dolman, Michael Johnson, and Andy Strominger. They will talk in turn, and I will give a brief introduction before each talk. And we will hold questions for the question and answer period after Andy's presentation, with all three speakers available to take questions. Our first speaker tonight is Shep Dolman. Shep is the founding director of the Event Horizon Telescope Collaboration, an astrophysicist at the Center for Astrophysics of Harvard University and the Smithsonian Institution, and a Harvard Senior Research Fellow. He is also the co-founder of the Harvard Black Hole Initiative. Shep focuses on problems, difficult problems, that require ultra-high resolving power. He pioneered instrumentation that enables radio interferometers to achieve the greatest possible resolving power from Earth's surface. And he used them to measure the size of the supermassive black hole at the center of the Milky Way galaxy, among other objects. He earned a BA in physics at Reed College and a PhD in astrophysics at MIT. Shep, the screen is yours.
Okay, thank you, Larry. Let me get things started here. Is that showing up clearly?
You're good, Shep.
Okay, thank you. So it's a pleasure to be with you here tonight, virtually, of course, given the circumstances. But again, a pleasure. I want to thank Larry, the PSW, and also the sponsors for hosting this year's lecture. And it's a privilege and honor to give this particular lecture. So I'm going to talk to you today about the Event Horizon Telescope. It's a global project that came together with a specific, focused, scientific objective in mind, which was to make the first image of a black hole. I think most of us know what a black hole is, but it's when enough matter is condensed into a small enough volume that at its edge, the gravity is so strong that nothing can resist complete gravitational collapse. It collapses to a point. And after that, there's an event horizon that forms around it, which marks the point where the force of gravity is so intense that even light can't escape. So anything that falls to the event horizon stays inside the event horizon. And it marks a causal boundary from our observable universe. Now, if we could make an image of this object, then we could test Einstein's theories of gravity in the one place where they might break down in the universe, or a likely place. We're making these black holes into cosmic laboratories that are really extreme to test our most fundamental theories. And more than that, we know that black holes now power some of the most energetic phenomena in the universe. So by understanding and observing black holes on event horizon scales, we might hope to understand those phenomena. So we have constructed an Earth-sized telescope, and I'll go into some detail about how we did that. And we have made these first images, and I'm going to tell you basically how this all came about. And first, I'm going to go to this object here, which is Hercules A. I'm going to motivate this by showing you an optical image. This is an object that is about 2 billion light years away. At its core, there's a 4 billion solar mass black hole that we believe is spinning. And one of the reasons for this is that when we look at this in the radio, we see something entirely different. We see an indication here that there is an explosive and directed activity in this, at the center of this galaxy. And it can only really be powered by accretion of matter onto a supermassive black hole. It's the only mechanism that we know of that can power something like this. To give you a sense of scale, these jets span 1.5 million light years across. They contain the combined energy of about 20 billion supernovae, 20 billion exploding stars. And they are shooting out in diametrically opposed jets from the north and south pole of a spinning black hole. Now, what would we see if we could look directly into that? That's what the Event Horizon Telescope project is all about. And to get us going, I want to talk a little bit about relativity and what that means. To the left, of course, you see a young Albert Einstein, who came up with a new geometric interpretation of gravity. Instead of objects exerting force on one another, he saw mass as deforming space-time and then objects would move through that space-time. And by solving a set of equations, you could determine the motion of any object in that space-time. Now, a very important prediction was made that light would be bent by gravity, and you can see that here on the lower right. Einstein reasoned that during an eclipse, when the moon passed in front of the sun, that stars' apparent positions behind the sun would deviate slightly because the path of light from the star to the Earth would be slightly bent by about 1.7 arc seconds. That's about 1/2000th of a degree. This is a very small effect. But in 1919, Arthur Eddington and colleagues famously went to Principe off the coast of Africa and Sobral in Brazil, and they captured an image of a solar eclipse. And the horizontal white bars you see are the locations of stars. And they did deviate by exactly Einstein's predicted amount. And overnight, he became a household name. And our understanding of gravity and the structure of the universe was changed. Now, just a year after Einstein developed his theory of general relativity in 1915, this man on the right, Karl Schwarzschild, solved for the first time Einstein's equations for a very concentrated point mass. And he found that for a mass that was extremely small, a point mass, there would be this boundary that I've already introduced called the event horizon, where even light could not achieve escape velocity. And that is the formula you see up at the top, this expression, 2 times Newton's gravitational constant times the mass of the object divided by the speed of light squared. And that marks the edge from which you can never return. So black holes were a mathematical curiosity, but then we began to realize that they were indeed out in the universe, the result of exploding stars that have gone supernova, and their cinders are dense enough they can form black holes. And also we find black holes that are millions or billions of times the mass of our sun in the centers of most galaxies. Now, what would a black hole look like if you could get very close to one? So there are a lot of computer simulations, such as these, which show that very close to the black hole, where there's a lot of hot plasma radiating very copiously in radio waves and other wavelengths, you would wind up seeing a shadow feature or a silhouette feature. And that's because of the severe light bending around the black hole. So the center dark region is formed by light that falls through the event horizon. And the light on the outside is warped geodesics or warped light paths around the edge. And typical of these kinds of images, you see it's bright on one side typically, then on the other side. That's because the gas on one side is coming towards us, so it's Doppler boosted and is therefore brighter. And on the other side is moving away from us at relativistic velocities, close to the speed of light, so it's dimmer. This asymmetry is seen in almost all the computer simulations that we have run. And most of the emission that you're seeing in these images come from synchrotron emission. That's highly relativistic electrons orbiting magnetic fields. And as the electrons orbit these magnetic fields, they give off radio waves. Now, what's most interesting about this is that the size of this shadow here is given by a relatively simple equation. The diameter of that shadow is the square root of 27 times the Schwarzschild radius. Now, that's pretty amazing. So we have a closed form solution for what the size of that shadow should be. And if we could measure that, if we could lay a yardstick, a meter stick, across that black hole, across space-time, we would have a direct measurement of the mass of that black hole. And we could test Einstein's theories at the black hole boundary. Now, what are we actually looking at? So I'm taking a page from here from a manuscript by Max von Laue written in 1921. 99-year-old manuscript, still very germane today. So we're reaching back and shaking hands with luminaries as we make this image of a black hole. And what I want to call your attention to here is that this black disk here is the event horizon. That's the 2gm over c squared radius marked by the black hole. But what really forms the silhouette is the photon orbit, which you see here in blue. This is the orbit where light can just orbit the black hole. And so when light streams off of there at a right angle and is bent by gravity from the black hole to our screen over here, this is where the Earth would be, you see this distance, this length here of the square root of 27 over 2. So the full impact parameter, the apparent size of this shadow, that dark region, is the square root of 27 times the Schwarzschild radius. And of course, Max von Laue got that right down here in the lower right circle. So we're looking for something whose dimensions are really set by Einstein's fundamental equations. Now this shows one of the best numerical simulations we have of the hot gas swirling around the black hole. And you can see it's marked by a little bit of emission inside here, which is in the front of the black hole, outside. But the main feature I want to call your attention to here is this bright circle. And you'll hear a little bit more about this, of course, in Michael's talk later. That is the photon orbit. And you can see on average it's a little brighter in the southern region here than it is in the north. That's because this black hole is oriented so that some of the material is coming towards us from below and away from us above. And so this is really the signature that we're after, this ring, this depression in the middle, and an asymmetry in the emission. Now, how do black holes shine? Like, why do they get so energetic, and why are they some of the most luminous objects in the cosmos? I want to illustrate that by just pointing out that if you drop an apple that weighs 100 grams a meter, you released about 1 joule of energy, and that's enough to power your cell phone for about a second. If you were to drop a piano off the Empire State Building, that's going to power a 60-watt light bulb for about 9 hours. So just to give you a sense. The reason that black holes can liberate so much energy is because there's no surface. The apple dropped at the same distance from the center of the Earth, 6,400 kilometers, would keep falling, and it would reach relativistic velocities near light speed. That same apple that could only power your cell phone for 1 second would release an energy equivalent to 10 to the 16 joules if it fell all the way into a black hole. And that is enough to power all the energy needs of Manhattan, not for a second, but for an entire year. So black holes are extremely efficient mechanisms for converting gravitational potential energy into luminous radiance. And how do those black hole jets form? Well, we think that magnetic fields that you see here twisting are anchored in a disk of material orbiting the black hole, or even the black hole surface itself. And they centrifugally accelerate charged particles from the north and south pole of either the spinning disk or the spinning black hole. And that's what gives rise to those jets that we see in the night sky. So now let's ask ourselves, which objects in the universe could we potentially take a picture of, and if they're a black hole? And the first object is the supermassive black hole at the center of our galaxy, called Sagittarius A star. And you can see here a radio image showing streamers of hot gas funneling into that white object, which we think marks the position of a 4 million solar mass black hole. And one of the best pieces of evidence for that is this movie, which shows stars orbiting that black hole. And you can see there, especially that yellow traced star makes a full orbit and has now come back around to make a second orbit since this movie was made. And the only thing that we know of that can cause stars to be tossed around like planets is a supermassive black hole. For this particular black hole, it's about 50 micro arc seconds across. That's the diameter of the shadow feature we'd be looking for. Its central mass is 4 million times the mass of our sun. But to see it, we would need to build a telescope that would be able to see the equivalent of a grapefruit on the moon. And so no typical ordinary telescope will do. And we had to be very creative about building an instrument that could see that. Now, the other object, and one that we'll be focusing on tonight, is M87, or Virgo A. And this is an optical image where you see a jet, much like the one that I showed you at the very beginning, coming from the center of this galaxy. And if we zoom in, though, so now we're looking at 3,000 light years on this bar here. And we take a snapshot of this, and we overlay it with a radio image. So now we've taken a radio image in the background, overlaid it on top of the optical image. We can see that they match almost perfectly. But now something interesting occurs. You see this ghostly image off to the left. And we realize all of a sudden that there is a jet in one direction, and there is also a jet in the opposite direction, but it's moving away from us. So the jet on the right is pointed almost directly at us, only 17 degrees from our line of sight. and it's Doppler boosted, so we see it enhanced in brightness. The same equivalent jet is moving away from us, but it is Doppler deboosted, very faint. We don't see it except where it runs into the intergalactic medium and creates a shock wave on the left. Now, as we look at this jet at ever more, at higher magnifying powers, we see that this self-similar jet continues on to the core. Now we're at 12 light years. Now we're at 4 light years. And this is the highest angular resolution image made to date of Virgo A, or at least until the Event Horizon Telescope targeted this object. And you're looking at 0.3 light years across. And the question we asked is, what would we see? What would we see if we were looking in that square there, that central few pixels? Now, it turns out that this image that you see here was made at a wavelength of 3 millimeters, so radio waves at 3 millimeters. We have to go to even higher frequencies in order to see through to the core. And that's illustrated in this movie that I'm going to show you. This is going to take you to the black hole at successively shorter wavelengths. So we're looking at a picture now at long radio wavelengths, and then we'll go all the way to 1 millimeter. And you can see that as we do that, the shadow slowly becomes clear. So it's only at this short wavelength that we can see through all the hot gas that is surrounding the event horizon. At this wavelength, the black hole becomes visible, but not at longer wavelengths. So we need to use these very, very short wavelengths to see through all the way to the event horizon. And you can see there the characteristic silhouette shape. Now, if you want to photograph a black hole shadow, then you need to build a telescope that has some pretty extreme parameters. And astronomers typically use this equation that the angular resolution of the smallest size of an object on the sky you can see would be the wavelength of light that you're observing divided by the telescope size. So either you want to make your wavelength very short, or you want to make a tremendously large telescope. And remember, the shadow size we're looking at is 50 micro arc seconds across. That's about a factor of 100,000 finer than Eddington needed in order to see that deviation of light by the sun. Now, we need to see through not only the hot gas near the black hole, and not only the interstellar and intergalactic gas that separates us from the black hole, but also the Earth's atmosphere. And it turns out that there's one wavelength that fits the bill, that lets us do all of these things. And that's about 1 millimeter wavelength. But if you put 1 millimeter into this equation, this is the wavelength that allows us to see all the way to the event horizon, then you quickly realize that to get 50 microarc seconds, you need a telescope that's at 10,000 kilometers across. So we can't build a normal telescope like this. This is the large millimeter telescope outside Puebla, Mexico. And these, of course, work by focusing a plane wave coming in off a very precisely machined parabolic surface so that all the light is reflected to arrive at the same time at a focal plane here where you can put your camera. And it's impossible to make a dish this size that could resolve the event horizon of a black hole. So we use something called short wavelength, very long baseline interferometry. And I still marvel at it. There's a little magic about it. But what we do is we basically split the telescope into two pieces. And we record light from the distant black hole at a radio telescope at one part of the Earth and a separate radio telescope at a different part of the Earth. And we use atomic clocks so that we can time tag the data to extreme precision. And then we record the data on hard disk drives, and we ship those hard disk drives to a central facility called a correlator where they're compared. So in this way, we mimic what a radio telescope does in a single dish format. Light, instead of light bouncing off the surface and arriving at the same time at the focal plane, we record the data with such precision that we can play that back later in a supercomputer and align them in time, and then combine the data as though we had a dish as large as the distance between these two radio telescopes. And this effectively allows us to make a telescope as big as the Earth, because now our telescope is the distance, the size of the distance between these telescopes. And of course, nothing beats the bandwidth of a 747 loaded with hard disk drives. So we load these up in boxes, we give them to FedEx, and they are headed to the correlator where we correlate them and process them. No internet on the planet is fast enough to get the data back in a timely way. So we spent a number of years building this array out. So we now have 8 dishes, soon to have 11 dishes. They range from the sub-millimeter telescope here in Arizona, the large millimeter telescope in Mexico, 2 telescopes, APEX and ALMA in Chile, 2 telescopes at the High Mauna Kea site in Hawaii, the SMA and JCMT. We have a telescope at the South Pole, and our European colleagues are joining in with the IRAM 30 meter in southern Spain. Now, all together, these represent little silvered elements of our virtual Earth-sized telescope. So we have not really filled in this telescope to the point where we could hope to make images. Thankfully, the Earth rotates. So during the course of a night, all of those telescopes move, they change in their look angle and their orientation with respect to the target black hole. And you can see on the right that each pair of telescopes gives us one data point. Each pair of telescopes gives us one bit of information that we can use to form our Earth-sized aperture, and that's shown here on the right. And over the course of an evening, we trace out enough of these virtually reflective threads to fill in enough of this telescope that we can make our images. So Earth rotation is absolutely part of what we do to make this Earth-sized telescope. Now, the other thing that you have to be aware of is that as we go to shorter wavelengths, the surface of our dishes has to be ever smoother because, of course, when you have the shorter wavelengths, any roughness on the dish is going to decrease its efficiency. So we are mostly looking at smaller dishes, and the signal to noise of our detections between 2 telescopes, it goes as the square root of bandwidth times the diameter of both dishes multiplied by each other. So the best way to increase your signal to noise, the best way to get a booming signal is to have very large diameter dishes. We can't do that. So we make up for that in large part by increasing the bandwidth. And what I'm showing you here in this plot is the rate at which we can record data streaming into our radio telescopes as a function of year. And you can see when we first started this, I've been doing this for some time, I guess, we were recording about half a gigabit per second. And now we were recording 64 gigabits per second. And remarkably, we have tracked Moore's law, which is this blue dashed curve. It's very rare to see cutting edge research instrumentation closely tracking commodity electronics. And that really is what has made this possible. We were able to use commercial off-the-shelf technology to build bespoke radio astronomical instrumentation. And you see what the whole system looks like to the right here. Banks of hard disk drives being recorded on, and electronics that digitize the signal from the superconducting receivers that lie at the focus of the single telescopes that are part of the array. So we had a ton of fun. I have to say that one of the reasons I got into this field was to go to mountaintops and bolt equipment into racks and to do new things. The first thing we did was we built out capability at the large millimeter telescope. You see here one of our grad students, Gisela Ortiz, adjusting the atomic clock. And there's a picture of the large millimeter telescope in the bottom right. Then we also outfitted the APEX telescope in Chile. And you can see here this strong red peak shows the proper alignment of the signals we record at the APEX telescope with the one at the South Pole, which I show you here. We sent a team down to the South Pole also to outfit this telescope, which was doing other things for this technique of VLBI. And then this is the IRAM 30 meter in Spain, and a detection shown here between Spain and Chile. And I'm happy to say that we were able to collect a treasure trove of data in 2017. We aimed all of these telescopes at the M87 black hole in the center of the Virgo A galaxy. And we took data for 4 days, and the weather was spectacular. Typically for astronomy, you hope to get good weather over 1 telescope. We needed good weather over 8 telescopes. And thankfully, nature cooperated. And we took some wonderful data. I want to give you a feel for how we model these data. What I'm showing you here is data from the entire array for one of these days. And I'm plotting it as the energy received on a pair of telescopes, that's the y-axis, versus the distance between the telescopes. And I want to point you to this feature where as you get larger and larger separations between your telescopes, you get this bounce. There's a null here, and then it comes back up again for longer baselines, longer distances between the telescopes, then it comes back down again. Now, we can fit these data, and if we want to fit this with a blob, just a kind of a Gaussian distribution, which is very symmetric, it's very difficult to fit that substructure with the Gaussian because this is the characteristic curve that the Gaussian would appear as on this particular plot. But if you have a disk, then the sharp edge of the disk causes a ringing and a bounce, but the second bounce here doesn't quite fit the data. It's when you start going to a ring that you begin to see how a ring morphology could start to fit this. And then, of course, if you look at a slight crescent structure with some asymmetry here, then you get a family of curves that fit it. So as soon as we saw these data without even imaging, we knew we had something that was quite spectacular. And then how do we image? Well, it turns out that modeling is pretty easy because we only have a few parameters to fit: the size of the ring, the width of the ring, some of the asymmetry in the ring. But if you want to make an image, then you have to map brightness onto many pixels. And we don't have typically enough data to do that. So what I'm showing you here is this is the kind of the fitting function, if you will. And the goodness of fit is related to data terms. So we fit the image to the data. We ask ourselves, does the data fit the image? But then we also enhance our imaging by using regularizers. We say, well, we don't have enough data to make a full image without enforcing some regularity on the image. So we require that it be smooth, for example. We require that it be positive everywhere. These are very light regularizers, but they help the convergence of our techniques very robustly. And now I'll show you what this actually looks like in real time. You're seeing here the fit to the data getting better and better. As these numbers get smaller and smaller, it gets better and better. And you can see in the algorithm locking in on that ring structure as it tries to fit the data, but also enforce some smooth structure. So from both the modeling perspective, we knew we had a ring-like structure. And then when we imaged, we saw robustly that we had that too. So for two different techniques, we were able to recover that ring structure. And this is the final image that we saw. And I just want to pause for a moment and say that this knocked our socks off. And I hope it's knocking your socks off too. You see here the three things that I signaled to you were the signatures here. You see this ring structure, which we take to be the photon orbit. We see the asymmetry, and this we think is the shadow of the black hole formed by that photon orbit around a 6.5 billion solar mass black hole. The reason this is so important is that it shows that if this is the photon ring, there are 6.5 billion, a mass that is 6.5 billion times what our sun weighs, surrounded by this photon orbit. So this is the best evidence for the existence of supermassive black holes that we know of. To make us feel a little bit small, to put this in perspective, this shows just how big this black hole is. Our solar system fits into this black hole many times over. This is a great cartoon by XKCD. And this is Voyager, the farthest person-made object from the Earth. So now let's ask, how did we make this image? Because it's one thing to model, it's one thing to unleash new algorithms, but there's also a human element here. So we wound up splitting up into 4 teams: Team 1, Team 2, Team 3, Team 4, largely separated by geography around the globe, but also by the techniques that we used. And the reason for this was we wanted to avoid groupthink. If for a result this important, for a result that would be this transformational, we wanted to remove any source of human bias. So these are the teams. We have Team 1. Here's Michael, who you'll hear from a little bit later. Team 2, largely centered in Europe. Team 4 in East Asia, and also Team 3 here in Europe. And very enthusiastic. Again, I want to reinforce the fact that to build a global telescope, you really need to have a global team. And the reason, as I like to say, that we split up like this is because it's very difficult to tell the difference between fried chicken and labradoodles. It turns out that artificial intelligence, even some people, can't really tell the difference. And you can fool yourself into thinking you're looking at a labradoodle when you're actually looking at fried chicken. And of course, it's even harder when you have chihuahuas and blueberry muffins. And this is a little bit of levity here, but this is really true. I've seen this happen in science when everybody convinces themselves that they're seeing one thing because they resonate and they bounce ideas off of each other in a closed environment. And so we purposefully split people up. So we all came together on July 24th in 2018, and each of the 4 teams that had not been in contact with each other showed their results. And you can see that there are some teams here using that regularized maximum likelihood method that I showed you before, getting a ring-like structure. And then 2 teams that used a more traditional radio astronomical algorithm called CLEAN also got the same ring-like structure. This was a watershed moment for the Event Horizon Telescope because 4 independent teams had come to the same conclusion. You can see the whole part of the team here in the basement of the Black Hole Initiative at Harvard University. A lot of smiling faces here. So then we put on our critic hats and we asked ourselves, well, are there any other ways that we can fit these data? And then we trained our algorithms on morphologies that were not ring-like. So we had some algorithms that we trained over here on a perfect ring, some on a crescent, but then we also trained our algorithms to return filled disks and doubles, which also have some of that same ringing structure on that plot that I showed earlier. And once that we had trained our algorithms on things that did not look like a ring, for example, the disk and the double, we still got these rings very robustly. So these are the final images that 3 different techniques in our collaboration came with from the April 11th data. This really showed us that we had a very robust finding, although you can see some differences here. You can see that azimuthally around the ring, there are some changes from method to method. And there is some uncertainty about the exact morphology azimuthally of the brightness around the ring here. But the most important thing is that this ring structure is very robust. Now, more than that, we got the same results for 4 separate days. So if it had been one day, we might have thought, well, we only have data and a good image from one day, but for 4 separate days, each completely independent data, we wound up getting the same morphology. And on the bottom here, you see how we filled in the Earth-sized virtual lens on each of the subsequent nights. And you could also ask, well, was that the only thing you imaged? And were there some other objects that you also looked at that did not look like rings? And indeed there were. This is a quasar, a very luminous black hole called 3C279. And it shows a completely different structure that is a structure that's expected from one of these quasars. You see the core here where the black hole is and a jet, much like the jets that we saw earlier from the 2 sources that we looked at. And you can see here that this source is far enough away that we can't hope to resolve the black hole at the center here, but we can use this as a calibrator. This is a source where the structure is known, and we get good confirmation across all 3 of these methods when we look at it with the Event Horizon Telescope. Now, I can't stress enough the importance of adding sites to our array. So when you have only 2 sites, as you see here, one in Mexico and one in Arizona, you really couldn't hope to say anything more than we have a brightness distribution that's completely symmetric. If you add another telescope, this is when you start to get higher angular resolution, but you still can't tell what the structure is. When you get an outrigger site here to Hawaii, then you get enough triangulation with different baselines that you're able to begin to see the ring-like structure. But it's only when you have the full array with outrigger sites on both sides of the central spine here that you wind up with a very good reconstruction that shows the ring. And how important is Earth rotation aperture synthesis? How important is the rotation of the Earth? And the answer is it's critical. So on the left here, you'll see a rotating globe, and I'll show you all of the baselines as they light up when we're taking data. The middle is the aperture as we fill it up, and on the right is that energy received versus distance between the telescope plot that I showed you before. And on the bottom, you'll see the 3 different algorithms, clean and the 2 maximum likelihood methods, working with just the data at that moment. And by the end, they'll have all the data so you get the best image possible. And you can see that as the Earth rotates, we get more and more data. We fill in more of the aperture. We start to see those nulls that I pointed you to before more and more clearly. And then you begin to see this ring structure emerge in all 3 of the methods. And then finally, the observation stops. So the Earth rotation is really critical for this work. Now we ask ourselves, well, how do we extract a size from this image, and how do we make the measurement of the mass? So one of the ways to do this is to measure directly from the images. So for example, we can sweep around the image like this, and we can get a histogram of the width of the image, the radius of the image, and we can estimate from each of the days that we have the size of this ring. And then so we get the diameter and the uncertainty. And the key thing here is that now we can use that equation that I showed you before. The diameter of the shadow is equal to the square root of 27 times the Schwarzschild radius, which only depends on mass. So now that we know what the diameter of the ring is, we can get a mass estimate. And just by measuring the size of this strong gravitationally lensed feature on the sky, we've measured the mass of the black hole to be 6.5 billion solar masses, to within about 15% or so. Let's pause for a moment. This is the first time that we have used general relativity to measure the mass of a black hole. And what's more than that, we can make a comment about the validity of general relativity around this black hole too. So what I mean by that is that there are 3 ingredients to looking at how well we have verified Einstein's theory by seeing this shadow. We know, for example, that we can measure the mass of this black hole by assuming that we've seen the shadow, and by assuming that the metric that we understand holds that the space-time around this black hole is the Kerr metric, and we can use that to predict what size we should have measured. And in fact, we get that size, we measure the mass, and what I'm showing you here is 2 other measurements. So you can also measure the mass of the black hole using stellar dynamics, or the motions of stars around the black hole, or you can measure it by looking at the motions of gas around the black hole. And you can see here that the stellar dynamics measurement of the mass peaks in its probability right on this shaded column, which marks the EHT measurements. So our mass agrees completely independently with the stellar dynamics mass. And there is another way to measure the mass of the M87 black hole by looking at the gas motions around that orbit the black hole. But at this point, we feel that these are probably including other effects. So it's harder to measure the mass of a black hole by looking at gas orbiting the black hole, because gas is affected by pressure and other forces, whereas the stars are really good point particles, and they are responsive primarily to the gravitational potential of the black hole. So what you see here is that our independent mass measurement agrees very closely with the stellar dynamics mass. And this gives us great confidence that we are seeing a black hole. It is described by the Kerr metric. The other important thing to notice also is that the circularity of the image we saw is completely predicted by the orientation of the jet from M87 and the expected appearance of this ring. So that also gives us great confidence that we're seeing a true signature of general relativity. Now, what comes next? We'd like to make these tests even more precise. So for example, we would have to measure the circularity of this image to within about 2% to really start to probe and make new tests of gravity. So we would like to add many new sites around the globe, filling in that Earth-sized virtual telescope. All the blue traces you see here land on new sites that we are hoping to build over the next 10 years. And we call this the next generation Event Horizon Telescope. And the reason this is important is because this would allow us for the first time to make the connection between the black hole and the jet that's launched from M87. So in these three panels, on the left, you see a computer simulation that shows what the black hole looks like in the inset. And it also shows the low surface brightness emission flowing from the black hole, powered by the black hole with those magnetic fields I showed you before. With the array we used in 2017, we can image the black hole, but we could never image the low surface brightness jet as it's launched from the black hole. But with the next generation EHT, we can get exquisitely high fidelity images, and we'll be able to trace the launching of this jet and address the great mysteries of how the black holes launched these jets and powered these galactic scale outflows of material. And we may also be able to leave the surface of the Earth. So on the left, you see the typical Earth rotation aperture synthesis building of the virtual telescope. But if we had Earth orbiters in low Earth orbit around the Earth, we would fill in that Earth-sized virtual lens very, very quickly and almost completely. And this would wind up giving us such high imaging fidelity that we could start to make real movies of black holes. So both the next generation instrument and space VLBI are aimed at creating real-time black hole cinema for the first time. And this is what we would be able to do. On the left, you see a model showing a movie of a black hole. In the middle is what we could reconstruct if we had a low Earth orbit satellite added to the EHT. And on the right is what we could do if we had a geostationary satellite and a LEO satellite and the Event Horizon Telescope. You can see that we can reconstruct all the motion of the plasma, all the motion of the hot gas around the black hole. And that is important because in addition to just the appearance and diameter and shape of the shadow, it's the period of orbiting gas around the black hole that can also test Einstein's theories. It turns out that the size and shape of the shadow is not very sensitive to the spin of a black hole, but the period of matter orbits around the black hole is very sensitive. So if we could make real-time black hole movies, we could test Einstein's theories in a whole new way. Now, this is a very large project. It started off very small. There was only a handful of us going to the tops of mountains and bolting equipment into racks and making these early measurements. And I'm just so thrilled that we are now well over 200 members representing 60 institutes from 20 countries and regions. This is a picture of only about half of us at our annual collaboration meeting that we held in Hilo. Currently, we're working all remotely, but we certainly hope to meet again very, very soon when this crisis has passed. It took us by surprise, the resonance of this project and this result with the curious public. But when we came down from our hotel rooms the day after the announcement and saw that it was on the front page of every major newspaper on the planet, we realized that this had been appreciated by the public in a way that we hadn't thought of. And I think really it is due in large part to the fact that we are a diverse team. We reached across borders without politics in mind. We developed relationships with experts across the globe. We combined resources from many countries, many continents, and we all focused on a problem that people had thought was impossible. How do you take a picture of something that struggles not to be seen, that is behind nature's best invisibility cloak? And we found a way. And that gives me hope that a lot of the problems that are facing us globally as humans can be tackled in the same way. And I'll just leave you with this image. This has been very inspiring for us, and I hope it has inspired you too. And I really anticipate Michael and Andy's comments. Back to you, Larry. I think you're muted, Larry.
I'm almost speechless. See, I was literally speechless there. Thank you for a really wonderful talk. I'm a little regretful we have to move on, but we do. And there'll be time for questions after Andy's talk. So again, thanks, Shep, for a great talk. Our next speaker is Michael Johnson. Michael is a Smithsonian astrophysicist, a lecturer in the Harvard Department of Astronomy, and an inaugural member of the Harvard Black Hole Initiative. He was a leader, among other leaders, on the Event Horizon Telescope imaging team that produced the first image of a black hole. Michael studies black holes and pulsars, the most compact objects in the universe. Among other achievements, he utilized interstellar scattering as a vast stochastic lens to study pulsars. His studies of active galactic nuclei using Earth-to-space interferometry achieved the highest direct resolution of astronomical objects in the history of astronomy. Among many contributions to the Event Horizon Telescope project, he developed new imaging methods that produce movies of rapidly evolving black holes. Michael earned degrees in mathematics and physics at USC and an MA and PhD in physics at UC Santa Barbara. Michael, the screen is yours.
Great. Well, thank you very much for the kind introduction. And it's really an honor to be here with you and also sharing the stage with Shep and Andy. So you've heard now the story of building this Earth-sized telescope to take a picture of a black hole. And in the years since that picture was taken, it's prompted all sorts of new efforts, including efforts on the theoretical side to better understand what we might learn from black hole images. So I'd like to just share the story of one project that emerged from the EHT discovery. And this is one that I did with Shep and Andy, actually. So Shep described a little bit about how the image of a black hole produces a shadow. But black hole images have other features that are rather extraordinary as well. And one is that a black hole will produce not just one picture of material near it, but actually an infinite series of images. So if you imagine, as in this cartoon, someone standing on the left of a black hole, you'll see an image of them over to the left of the black hole. And that's from the light that came more or less straight towards you. But what's rather surprising is that you'll also see an image of them on the right of the black hole. And that's from the photons that went from the person, then behind the black hole, and they got bent so strongly by the black hole that they then were twisted, and so they went around the back of the black hole before reaching you.
So, Michael, are you sharing your screen?
Oh, I'm so sorry. Let's see. Does that help?
Yeah, we haven't seen any slides to date yet.
Well, this is the first critical one. So thank you for pointing that out. Good. So as this cartoon shows, this person, this hypothetical person on the left of the black hole, you'll see that direct image, and then you'll also see this the second image of them on the right for the light that passed behind the black hole. And then you'll see yet another image over here, and that's from the light that went from the person, then around the front of the black hole, and then all the way behind it, and then back to the front and to you, the distant observer. So I don't think I can really describe this net effect better than Charles Darwin, actually. Not the naturalist, but his grandson, who wrote, this is what advance. Each star, in addition to its direct image, will show a series of faint ghosts on both sides of the black hole. There will be a ghost on its left, just outside 3 radical 3m, where m is the mass. That's that formula Shep showed. Furthermore, there will be secondary ghosts on both sides, still closer to 3 radical 3m, which come from rays that have gone a complete circle around the black hole before escaping to the telescope. The successive ghosts of a sequence crowd together more and more closely to such an extent as exactly to counterbalance their increasing feebleness. And then he added, this result seems to have no practical importance at all. So we'll come back to that at the end. So we've seen this image now from the Event Horizon Telescope, this sort of blurry donut on the sky, and we don't think black holes really look like that. If we could see with perfect resolution, we actually think that we'd see a much sharper ring called the photon ring beneath that image. So that's blurry, not because black holes are blurry, but just because we're pushing our instrument to its absolute resolution limit. Now, the photon ring is the manifestation of the same property that Darwin was describing. It's just now, instead of having a person or a star on the side of the black hole, we have it surrounded by any sort of material. And so, so all that light around the black hole is lensed into a ring. So this ring occurs because of these spherical photon orbits. It occurs because of this special property that light can be trapped on orbits around a black hole and can loop around many times. Now, the photon ring has a number of very important properties. So first of all, we discovered it should have about 10 to 20% of the total image flux. So that means this is not some negligible feature in an image. It's actually quite prominent, and it has a lot of energy coming from it. Now, the second important thing is that the photon ring encodes the size and shape of the photon ring encode the black hole's space-time. Now, black holes have a rather peculiar property that they're completely characterized by just two things. One is the mass, how much material fell into the black hole. But then they have a second property, which is whether or not they're spinning. So if you can imagine taking a black hole in nature, you could feed it some angular momentum, and then it'll start rotating. And you can spin it up faster and faster, but there's actually sort of a cosmic speed limit at which you can't, by any known physical mechanism, accelerate it anymore. And so what we tend to do is we'll express the spin between these two limits of not rotating at all, and then this maximal cosmic speed limit is 1. And so you can tell from this that black holes are these really elemental objects, completely described by just these two numbers. You know, it's really extraordinary. They can be made out of anything, and they shed all of that information and are left with just this pair of numbers, mass and spin. And so the great astrophysicist Chandrasekhar wrote regarding this that in my entire scientific life, the most shattering experience has been the realization that an exact solution of Einstein's equations of general relativity provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. So this is one of the most profound truths in physics. And if we can look at the photon ring, maybe there's a way of testing whether or not black holes really are described by just these two numbers. So the question is, how would this spin affect the image of the black hole? Okay, so here's what the black hole shadow and photon ring would look like in the case of a non-spinning black hole. It's a perfect circle, as you might guess just from symmetry. And so now let's repeat that exercise. Let's just spin up the black hole and see what happens. So as we start the black hole spinning, one thing that happens is the shadow actually shifts over to the right. But as it's shifting, it's also changing shape. So it's getting squeezed in the horizontal direction. And at the highest spins, that left-hand side of the black hole actually flattens. So it's this family of curves. They're not perfect circles. And if we could make a very high resolution image of a black hole, we could read the spin of the black hole off the shape of its photon ring. So it's a very intriguing possibility. Okay, so the other property of the photon ring that's really rather remarkable is that the emission radius gets mapped to the image angle. So naively, you would think emission at the top of the photon ring is coming from material above the black hole, and emission at the bottom of the photon ring is coming from material below the black hole. But instead, it's actually a sort of holographic mapping, where different angles around there are actually telling you about different distances from the black hole. The bottom is from material that's close to the event horizon, and the top is from material that's further away from the event horizon. So if we could make this image, we would be able to unwrap it and see this tomographic probe of the three-dimensional distribution of the emitting material in the space-time very close to the event horizon. So the photon ring is this incredibly rich object, and we're still learning about it. But the problem is it really seems almost hopeless to actually access this observationally. So first, at low resolution, the effects of relativity that we're seeing here are really dwarfed by astrophysical uncertainties, just all the swirling plasma around the black hole. And so to really get at these relativistic signatures, we need to improve the resolution of EHT images by maybe a factor of 10 to 100. And there's just no plausible way of doing that in the current observing paradigms. So what can be done? Well, it turns out that just as Darwin described for this star, we expect that the photon ring is really a stack of subrings. So the first thing that we'll see, the dominant subring comes from light that moved near the black hole and is just weakly bent by it. That forms this image that we're just calling n equals 0. And in addition to that, there will be light coming from photons that looped around the black hole before reaching us. And in order to do that, they have to be shot from a very precise region. So these photons actually pile up on a much narrower ring around the black hole. Now, you can also imagine light that has to go around the back of the black hole and then front and then all the way around again. And so this is the n equals 2 image, and this will pile up onto a yet sharper ring. And so the image that we see isn't actually just a single ring, but it's this stack of increasingly sharp subrings. And their sum is what's forming this single photon ring feature that we see. So this is sort of analogous to layers and a tiered wedding cake. And this is where all the really rich information is encoded. And what's remarkable is if we go back and look at that image from before, this is an image from a simulation. And it wasn't obvious that these subrings were here, but if we look after the fact, if we just trace across it and look at emission profiles as a function of distance from the center, you'll see that indeed, this image has these different peaks of emission corresponding to the different subrings. And if we zoom in on those peaks, they break into even more peaks. So you can see all of the distinct subrings here cleanly separated if you could just look with extraordinarily high resolution right across the edge of that ring. Now, the problem is that even with this perfect image that I'm showing you, these features are sort of hopelessly faint. Right? How could we possibly create an instrument that could see something that is so delicate? And here, interferometers come to the rescue. So as Shep showed you, ordinarily when we have interferometric data, when we take these telescopes and sprinkle them across the Earth, it takes a lot of work to then interpret what those data are telling us. We have to use model fits or imaging methods in order to make sense of it. But the difference here is that the photon ring is such a simple signature that on long baselines of an interferometer, it filters out everything else in the image. It locks onto that photon ring, and it gives an extremely simple signature, just this damped ringing periodicity. So this is a really special feature. It arises in black holes and really doesn't arise in any other object we've ever studied in astronomy. Now, ordinarily in interferometry, you would only get to sample one point on here for every pair of telescopes. And then you have to wait for the Earth to rotate or you have to add more telescopes to see more points. But we have another trick that we can play. And that's that in interferometry, all you care about is the distance between the telescopes in wavelengths. And so you can actually scan out at different baseline lengths using a single pair of physical telescopes by observing at many different frequencies. So we think that a single baseline could actually see this damped periodic oscillation. So a single pair of telescopes might be able to see these subring signatures. Now, here, the periodicity that you see with these very long baselines corresponds to the diameter of the ring. And what I'm showing here, the red and the blue are actually baselines. One would be a horizontal baseline and the other would be a vertical baseline. And so these two baselines are actually seeing the two ring diameters along their direction. And so what's extraordinary is that you can see that these aren't quite the same. Or if you look down here, you'll see that these red peaks are sliding to the right of the blue peaks. So that's the reason that's happening is because this black hole in this simulation is spinning. And this produces about a 1% difference in the diameter in the horizontal and the vertical directions. It's imperceptible by eye, but you can read the spin straight off this figure. Somehow, almost miraculously, interferometers are much better at studying the properties of the photon ring just natively in their interferometric domain than we can, even with perfect images. Now, as you go to even longer baselines, something happens, and that's that once your baseline gets long enough, you'll start to resolve out the rings. So as you go to a very, very long baseline, you'll stop seeing the low order subring, and then the next one will kick in. So on these shorter baseline lengths, all they'll see is that n equals 1 subring. And then as they go to longer and longer baselines, they'll resolve it out and they'll just see the n equals 2 subring. Go to longer and longer baselines, so resolve it out and just see the n equals 3 subring. So again, interferometers give us this gift where for the image, all we see is the stack of all these subrings and they're hard to decouple. But an interferometer will naturally decouple these subrings. So if we're able to make a series of very long baselines, we would actually be able to study these subrings individually, and their relationship encodes special properties of the spacetime near the black hole and tells us about the stability of the photon orbits. So really, black holes are giving us a remarkable gift. You know, this is a type of feature that seems impossible to study with current technology. And yet, the black holes are also giving us an opportunity to study them in a completely new way. So they allow us to decouple the relativistic effects from astrophysical effects by going to these very long baselines. The longest baselines will only see the relativistic effects of the photon ring. It's such simple structure that a single baseline is enough. We don't have to build a whole suite of telescopes like we had to for the EHT. And we think that because the photon ring has so much power, there's actually a fairly strong signal when you go to these really long baselines. So this is an opportunity for an extension of the EHT to space. And with this extension, we think that we could study not just the black holes we were already looking at with much higher resolution, but we could actually estimate the masses of thousands of black holes. So here's just one example similar to what Shep was showing where we can couple this new very high resolution with the existing ground array. So here's this simulated image. The top here in the center is what we would get with the current EHT just using the ground data. The bottom is what we would get just using a single very long baseline in space. This is in a geosynchronous orbit, and so it only would see the photon ring. And then if we couple those together, then we can see both the astrophysical elements of this image and the GR, and we can start to study this very precisely. So really, black holes have now moved from being just the realm of theoretical imagination to being a primary experimental focus in astronomy. You know, we've seen these direct images of the supermassive black hole in M87 with the Event Horizon Telescope. These are opening all sorts of new possibilities for us to study. We're learning more and more about how black holes imprint their properties on images. And this gives us a way to test whether our theories of black holes are correct. So we're doing direct tests in a regime where we know that our physical theories must eventually break down. And most exciting, you know, this is something that we can actually study. So we're starting to get a better sense of real experiments that we might be able to do in the next decade or two that would improve the resolution of the images you've already seen by a factor of up to maybe 100. So we could really put Einstein's theories to the test in a whole new way. So thank you so much.
Thank you so much, Michael, for that talk. We will move on to our last talk. Our final speaker is Andrew Strominger. Andy is your professor of physics and director of the Center for Fundamental Laws of Nature at Harvard University. Andy's made many significant contributions to theoretical physics in the areas of quantum gravity and string theory, among others, including on the stringy origin of black hole entropy. He earned his AB at Harvard, his MA at UC Berkeley, and his PhD at MIT. And before I turn over the screen to Andy, let me make a short remark. You can ask questions in the Q&A, but we want to hold the answers for the Q&A period so that we can share them with the YouTube audience because they can't see the Q&A on Zoom. So feel free to put your questions in, but the answers will come during the Q&A. So thanks so much. And Andy, the screen is yours. Are you there? Ah,
Am I there?
you're there.
Okay. All right. So it says the host has asked you to start your video. Has it started?
You need to start your video. You need to get rid of that red line.
Am I on?
Yes, all good.
Okay. So it's an honor. Thank you, Larry, for the invitation to speak here. And it's especially an honor to be following Shep and Michael, who've done such amazing work recently. And okay, there's a problem here. Okay, can you see picture 2? Hello?
Yes.
Yeah, we can see it.
Okay. So I'm going to try to talk about black holes in a broader context. Black holes have come to center stage in multiple areas of modern science. So the imaging of black holes have, as we've just heard, has reached spectacular new heights. And at the same time, there's an ongoing theoretical activity understanding the properties of black holes. Black holes are of interest to mathematicians, to theoretical physicists, of which I am one, to historians, to philosophers, gravitational wave physicists. They're incredibly interesting for many reasons. And in this brief talk, I'm going to talk about one thing which has been a central theme in modern physics for the last 40 years, and that's the famous black hole information paradox, and how those efforts have dovetailed with recent observations from the Event Horizon team. So understanding black holes is not something which you do in a 3-year NSF grant cycle. It's an endeavor which should be measured in centuries. Indeed, it was a full century from more than a full century from the prediction of black holes till their actual direct observation a year or 2 ago. And black holes are so interesting because they epitomize what we do not understand about the physical universe. So as Shep mentioned in his talk, black holes were discovered more than a century ago by Schwarzschild, who solved the Einstein equation. And he solved the equation, he found an exact solution. You thought that might have cleaned up the subject. But no, the debate went on for half a century. And the structure of this solution was so strange and confusing that Einstein himself, in a published paper in 1939, said that black holes cannot exist. And I've given here his reasoning. The Schwarzschild singularity doesn't appear because matter can't cross it. Completely wrong statement. He would flunk any course in general relativity now for saying that. And people argued about this for 60 years. And after about 60 years, they began to understand through work of Penrose, Hawking, Thorne, Bardeen, Carter, many other people, began to understand what a classical black hole was. This occurred in the 60s and early 70s. And now, of course, we think we actually see them. So for some time, there has been little doubt that black holes exist, and we've understood what a classical black hole is. And we could say, and Shep and Michael both described this, that a black hole is exactly that. It's a hole from which nothing can emerge, not even light, so it's black. And anything crossing into the black hole never comes out again and just dissolves into nothingness. And unlike stars, which have all kinds of intricate features and coronas and so on, they have no features except for the mass and the angular momentum. This caused John Wheeler to coin the famous adage, black holes have no hair. They are the simplest, most essential objects in the universe. This was how we thought about black holes in 1974, just before Stephen Hawking's famous work. And Hawking considered what happened when you applied the uncertainty principle to quantum mechanics to a black hole. And in quantum mechanics, locations of things are a little bit uncertain, including the edge of the black hole, which moves around a little bit and allows light to escape. And the escaping light is famously called Hawking radiation. It comes out in the form of black body radiation at a temperature known as the Hawking temperature. It's Planck's constant of quantum mechanics divided by 8 pi times Newton's gravitational constant times the mass of the black hole. This formula is inscribed on Hawking's headstone in Westminster Abbey. It's a central formula in modern physics, and it's one which we do not understand. It has the form of giving the temperature as a function of the mass or the energy of the black hole. And such relations are known as thermodynamic relations. And it's of the general form of the laws of thermodynamics that were discovered theoretically and experimentally in the 18th and the 19th century that govern the behavior. It tells you that if you turn on the burner on your gas stove under a pot of water, how fast you can bring it to a boil. That's a law of thermodynamics. Now, in one of the most breathtakingly beautiful developments in all of science, Boltzmann showed that the laws of thermodynamics are actually just the laws of statistics and probability in disguise. And in order to show this, he had to assume what was then a very controversial assumption, that everything is made of molecules. And if you study the probabilities of molecules in various configurations, you can derive from that how pressure behaves as a function of volume and how temperature behaves as a function of energy. And a key ingredient in Boltzmann analysis was the entropy, or equivalently, the information, the number of configurations that are accessible to, for example, a bunch of molecules moving around in a box. And nowadays, we would measure information in gigabytes. So if you have a computer or an iPhone, it has some bits in it which can be up or down. And so there are some number of configurations that your iPhone can have. And that's measured in gigabytes, which is a unit of entropy. Okay, so applying Boltzmann's reasoning about thermodynamics coming from statistics enable us to infer how many gigabytes there are in a black hole. And the answer is very strange. The number of gigabytes in a black hole is equal to the area of the black hole divided by 4 times Newton's constant times h bar. And this is a universal formula which applies to every shape and variety of black holes, spinning black hole, not spinning black hole, with charge, without charge, whatever. It's a universal formula. It's also an incredibly interesting formula because it involves information theory, it involves quantum mechanics, it's got Planck constant, it involves gravity, and it has all of these things together. Yet, as I will explain, we don't understand this formula, even though we're sure it's true. But I'd like to pause to say that it's a very, very big number. All the gigabytes in the Google data banks could be stored in a black hole that's 10 to the minus 24 millimeters, very, very small black holes. So, M87 or Sagittarius star just can store an incredible amount of information. They are the best hard drives in the universe. And in fact, we believe that black holes are exactly that, the best hard drives you can possibly make, that they can store more information than, and it's a law of physics that you cannot store more information in any given region than you can in a black hole. Now, this is actually trouble for Moore's law, which says that the amount of information you can store doubles every 3 years. In 300 years, we'll have so much information in such a small area that it will exceed the black hole bound. And at that point, if you want the computers, all computers will have to be black holes. And Shep, talking about keeping up with Moore's law in his talk, if he keeps going for another 300 years, which I'm sure that he will have to be shipping black holes in his FedEx boxes around in order to do even more refined, spectacular measurements of all the wonderful things that we see up in the sky. Okay, now if you were listening carefully, you heard me say two things, which were completely opposite. One is that black holes are the simplest object in the universe. They have no structure. They're just holes in space. There isn't even a place to store computer chips. And the other is that they're the most complex objects in the universe, that you could store all the information needed for the Event Horizon Telescope in a tiny, tiny, tiny black hole. So that is the puzzle. How can a black hole simultaneously be the simplest objects in the universe and the most complex objects in the universe? Now, this puzzle gets even sharper when you think about making a black hole by collapsing stars and then letting it disappear by Hawking evaporation. All the information in it will be destroyed. That means we don't have laws of physics. We only have probabilities for things. Now, this is deeply concerning to all physicists, and people have tried to understand how these basic facts can be reconciled for the last 40 years, and it has caused many, many sleepless nights, I assure you. Now, there must be a resolution of this puzzle because we believe the universe is consistent, but we haven't found it yet. But in our efforts to find it, we've run into many surprises, and we've learned some very surprising things about the nature of quantum mechanics, gravity, and space-time, and we've learned the kind of depth of this problem. And it's been very fruitful to think about it, even without yet having solved it. And it's taken many twists and turns, and one of the important ones involves string theory, which I'm about to tell you about. Now, string theory is supposed to be a consistent quantum theory of gravity. We don't know whether it describes the universe or not, but it's supposed to be mathematically consistent. And several decades ago, we used string theory to pull off what seemed at the time an impossible trick. to find a description of black holes in string theory that was both, that you could describe it, had what's called two complementary dual descriptions. On the one, in one limit, it looked like a black hole, and the other limit, it looked like a complicated object that could store a lot of information right on the event horizon. It's called a holographic information plate on the event horizon. It's kind of like a two-dimensional hologram storing the information in a three-dimensional object. And this reconciled mathematically the puzzle of how something could be, from one perspective, the simplest object in the universe, and from the other perspective, the most complex object in the universe. The problem is, we don't know if string theory is right or not. We're not going to, even with fantastic experimentalists like Shep and Michael, we're not going to determine it experimentally soon enough for me. Black holes are big objects. They're out there. We want to understand how M87 and Sagittarius star store the information that Hawking told us they must be storing. Now, if string theory found a way to do it, it might be that the mechanism in string theory could be operative in the real world. And moreover, we would like to show that a mechanism like that is operative without assuming all the structure of string theory. Now, it turned out that the essential ingredient was something called a conformal symmetry of the Einstein equation, a new symmetry of nature that appeared very near the horizon of the black hole. And this symmetry appears near the horizon of a very rapidly rotating Kerr black hole. These are, in fact, the simplest of all the black holes, the ones that are rotating around. Michael referred to it as a cosmic speed limit, the ones that are going right at the speed limit. And the cosmic speed limit, of course, is the speed of light. So the horizon of the black hole can't go around faster than the speed of light. And these kinds of black holes have the same symmetry that was used in string theory to explain the complexity, simplicity duality. Now, physicists love symmetries. In fact, their love can be measured in dollars. We just spent tens of billions of dollars to see the origin of the electroweak symmetry at the Large Hadron Collider in CERN, the Higgs boson, to see how the symmetry was broken. And here we have a new symmetry of nature that is arising near the edge of the black hole, which Shep and Michael have just imaged in a telescope. And now the symmetry occurs. Here's a picture of a black hole with an accretion disk around it. My pointer, unfortunately, is not working, so I can't point it, but right in the middle there on where the black hole is, right near the horizon there, is where this symmetry becomes manifest. So now we want to ask, what are the observational signals of this extreme conformal symmetry of Kerr? Can we see it at the Event Horizon Telescope? And is M87 rapidly spinning enough? Well, I was in the process of trying to understand this, this incredible picture was produced. I cried when I saw it. I'd been working trying to understand black holes for 30 years. I was pretty sure they existed, but it turns out, as I realized when I saw the picture, you're not completely sure until you see a picture. And it's nice to know that something you've been working on for 30 years actually exists up there. There it is. We want to understand it. And what we want to understand everything we can about it. Now, can we see the conformal symmetry that I was talking about? Well, we analyzed carefully. I won't explain this in detail. The polarization of the light that will be coming out. Turns out that this is going to can be seen in principle, but we need a couple of orders, 3-4 orders of magnitude improvement in the resolution. And as the data came in, it seems like we're not going to be able to see this anytime soon. But as I got talking to my experimental friends, it turns out there's another. So interfacing with the observers makes you think about things in new ways. And it turns out that there's another potentially related kind of conformal symmetry, which we hope will be observed in the next decade. And this is the picture that Michael showed you on the first transparency of his talk of the multiple images. These images are self-similar images, and they're related by a symmetry. And it's another kind of conformal symmetry which scales not to the horizon of the black hole, but to the photon ring, which gathers all the images together. And this symmetry, this conformal symmetry, as Michael beautifully explained, we actually do hope to see in the not too distant future, and for far less money than it cost to see the electroweak symmetry restoration at the Large Hadron Collider. So I want to conclude there. The road to understanding the laws of physics, and especially black holes, is full of twists and turns. I didn't expect that they were going to image a black hole so quickly and so precisely. We didn't expect string theory to enter into the study of black holes in the way that we did. There are many twists and turns in the road. We can only see a few bends ahead, but it's a lot of fun, and we're moving forward. So thank you very much, everybody.
Thank you very much, Andy. Really good closing talk. Certainly, black holes have got to be among the most stupendously interesting, surprising.
They sure are.
Objects that I think couldn't really have been imagined without Einstein's equations to play with. But we now have time for some questions and some answers. So if Shep and Michael will come on screen. Oh, we had Michael and we lost him. We have Andy and Shep. Okay. So I'm going to take questions off the Q&A. I guess you can kind of see them, but I'm going to read them out loud so that the YouTube people. So,
Yeah, I already started to answer one.
So let me repeat the question.
Sure, yeah.
Okay, so let's start with Colin Albert's question. He's really asking what are the parameters of the LEO and GEO satellites that you would like to have in orbit? How big do they have to be? What kind of instrumentation do they have to have in order to do some of the things you want to do?
Okay, I answered partially before I realized we should be doing this orally. I'll do part of it, and I think Michael probably wants to chime in here too.
And he wanted to know particularly about microsats and small sats.
Yeah. So it turns out that because we have some very large telescopes on the Earth, if you were to make interferometer baselines anchored on the Earth with a large telescope, and then have a small diameter telescope in space, that's viable. But even there, you run into a problem if your telescope is too small, because then you just don't have the signal to noise. You don't have the detectability on that baseline. So we've estimated that you probably need at least a 2-meter diameter dish, if not 3 or 4, to make something viable in orbit like that. It might be possible, as Colin suggested in the chat, to phase up or to fly a swarm of small dishes like that to overcome the diameter problem. But that creates problems of its own, because then you have to fly them in formation and phase them up in a certain way. So so we're thinking that it would be, you know, above 2 meters, probably 2 to 4. And Michael's been thinking about something that might even go out to like 1 million kilometers from Earth.
Yeah, I think it's worth noting these are radio telescopes, so the problems of making them maybe are a little different than something like Hubble. So having multiple meter-sized dishes might that be a little easier for a radio telescope than for an optical one? Or am I all wet on that?
No, you're right. It's still hard to get them in space, though. You might think one solution would be you can deploy radio telescopes. And the ones that have launched in space so far, they do this. They have these carbon fiber petals. But again, it's this balance, because we need, its radio wavelengths are very long compared to optical, but the ones that we're observing at are very short compared to most radio telescopes. So you need to have these very precise surfaces. So this is a big engineering challenge.
Yeah, one of the things we're hoping to do is potentially to piggyback on existing missions. So if there was a telescope already going to, let's say, the Lagrange point, which is 1 million kilometers away, then we might be able to just add a little bit of equipment to it to allow it to work in a VLBI sense, and use the telescope that's already going out there anyway for other purposes, and have it do something in addition to what it was originally planned for.
So you think you could piggyback on the web, but they'll never let you do that?
We're thinking that there's a project called the Origins Project, which is going to put a 6-meter dish at the Lagrange point about 1 million kilometers from Earth. So we're thinking about that one.
Okay, let me say my director here is frantically telling me that I should tell our audience on the Zoom that they can use their the hand feature, raise their hand if they would like to ask a question. And then we can call on them and they can ask their question. We have another question here from Federica Durama. And rather than me trying to read that out loud, maybe you can try to translate it and give a reply. I'll give it to Shep first.
Okay, I'm trying to think, which one is this?
Have you thought of using data in more dynamic ways where the model determines which additional data to use to improve accuracy? I think as you increase the number of telescopes in your array, shipping crates of hard drives is not scalable.
Oh yeah, I'm not sure if I get the sense of the question, but certainly what we're doing now is we're getting a very good idea of where new telescopes would go to fill in an optimal sense, the Earth-sized virtual telescope. So up to this point, we've had to go and use telescopes that already existed. And we brought the equipment that I showed to those sites. But in the future, we might hope to build entirely new telescopes, potentially smaller ones that could be rapidly deployed to precisely the location that would fill in the Earth-sized telescope in the best possible way. And in that sense, we're using some of the data we have now to plan for growing the EHT into the next generation instrument.
Thank you. Tim Thomas, a member, would like to know, do all black holes, regardless of their size, have these photon rings? And if small black holes have these energetic rings, why haven't we seen them before? Or have we? Well, I think you probably answer that pretty directly.
Yeah, all black holes have them. It's universal, and the only difference for a small black hole is the photon rings will be smaller. So the EHT image, this is the first time we've ever seen a black hole, and this is for a black hole that's about 6.5 billion times as much mass as the sun. The typical small black holes that are close to us in the Milky Way have a mass of a few times the sun, so they're 1 billion times smaller. So these things would be, we would have to improve the resolution of the EHT by a factor of 1 million to be able to see these photon rings. So we think they're just very hard to see.
Very hard to see. Again, if
But
you,
somehow weirdly not impossible. At first, it seemed like it would be impossible, right?
hence
So there,
black holes.
well, Shep showed that movie of, it's not enough to have perfect resolution, right? In that movie that Shep showed, you have to go to the right wavelengths, otherwise it's opaque and you don't see all the way down to the black hole itself. So it's not just about getting high enough resolution. And I think at most of the wavelengths where we do these types of techniques, even for much higher resolution, you wouldn't be able to see all the way down to the black hole for the typical emission we see from the stellar mass ones.
Although I think that one of the cool things about what Michael is thinking about and what Andy is thinking about with the photon rings is that if you had a really long baseline out to L2, then you get a lot of black holes that way. And Michael said this very clearly. When you increase your angular resolution, you can look back at many black holes across cosmic time, and you wind up bringing into focus tens of thousands, hundreds of thousands, maybe even millions of black holes. And then you can start to do population studies. So sometimes you want to look for your keys where the lamplight is, and in this case, if we got that one long baseline, we could do a heck of a lot in population studies of black holes that we can't do now.
So again, if you would like to ask a question directly, you can do so by raising your hand, and we'll arrange for you to ask.
Here's a question directly for Andy. Andy, can you see this?
I can see it, Shep. I'm ready.
Oh, go do it.
Directly for me. Which one?
Oh, it says, question for Professor Strominger. With regards to strings, you and Vafa had shown that you could go from microstates to compute thermodynamics of the black hole. Hawking's equation doesn't that say something about how string theory might be more interesting, and perhaps a way to test it in some ways might be looking at various black holes? I can't quite get the feeling of it. Maybe you can.
Well, when he's asking, so when Vafa and I first used string theory to understand the information paradox, Hawking's puzzle, it was a very complicated calculation, and we thought it might be evidence for string theory. The fact that string theory was the only thing that could resolve this puzzle made me think, okay, this is not, it's not like seeing it, but it's like, no, in a quarter century, nobody else figured out anyway, this might be evidence for string theory. But as time went on, we found simpler and simpler ways of doing the calculation. And ultimately, we realized that all that mattered was the symmetry. And that the way we did it in string theory was sort of the stupid bulldozing ahead way. We got the answer, but it had a lot more detail than was needed. But it gave us the idea of how to address the problem of methods to address the problem in the real world. So it was proof that string theory is useful to thinking about for getting new ideas for understanding the physical universe, but not proof of string theory as a fundamental theory of nature per se, or even very strong evidence. That's how we look at it now.
I have a question from Michael Moore, a member. He says, I note that Asia seems to be missing from your present array. Can there be assets that can be added there in the future?
Yeah, I'll take that one. So certainly one of the key things about this technique that we're using, very long baseline interferometry, is that both antennas have to be able to see the source at the same time. And it turns out that there simply are many telescopes in the West. We could start to think about adding telescopes in Asia, but they won't have mutual visibility with some of the key telescopes in the array. Now, that doesn't mean we're not going to do it, because we foresee a time when we'll have telescopes that girdle the entire Earth, and we'll be able to observe our our targets 24 hours a day with kind of a rotating network. But we just haven't built them in Asia yet. But we're actively looking in India right now, in China, and in parts of Russia. So I think that's going to come soon.
The next question comes from a YouTube live chat. The question is from Neil Umfalo in Medellin, Colombia. He wants to know, and I quote, and you guys can see this, what do you think ADS/CFT says about the universe?
I guess that question is probably for me, and hello to Colombia. So ADS-CFT was, I didn't use those words, but it was one of the slides in my talk when I said there were two ways of thinking about black holes. One is that the hologram that lives on the horizon, the holographic plate on the horizon, and then the image, the two different descriptions, the complex description and the simple descriptions. So ADS-CFT refers to two different ways of describing the same thing, which is, it's often very useful to have two complementary methods of describing the same thing. And yes, I think that everything ADS-CFT came from studying black holes. And it's something we learned along the way of trying to understand these objects up in the sky. And it looks plausible that this kind of relation is a basic property of our universe, that there are different complementary descriptions, the boundary and the interior. We don't know yet, but we'll keep going till we figure it out.
Okay, here's one for Michael. The one about what does Hollywood get right or wrong about black holes?
For me.
Oh, yeah, I think so, Michael.
Well, it's kind of interesting, actually. Kip Thorne is a famous relativist, and he was heavily involved in the making of this movie Interstellar, which went to extraordinary lengths to actually simulate in a realistic way what black holes would look like. So there are these scenes in the movie of people going into a black hole, and at least the process of creating the image has a lot of truth to it, with a few artistic liberties that then go to sort of absurd levels once he actually enters the black hole. So I'd say Hollywood probably has little to be proud of in their depiction of the black hole, with a few notable exceptions. I don't know. I appreciate the imagination, which, while not always being scientifically rigorous, certainly I think mirrors the wonder that they create for all of us on this call, while not necessarily getting the mathematical details correct.
Well, I'd like to comment on that one too. I liked Interstellar so much that I took my general relativity class to see it. And there's one scene in there where Matthew McConaughey is trying to escape from the black hole, and he has to eject something counter to the spin of the black hole. Now, Shep talked about this, about how energy is extracted from black holes, how they power the signals in the sky. And I think that comment about how Matthew McConaughey was going to escape from the black hole can't have been understood by more than 100 people out of the millions that saw that movie. So they got some things really right in that movie, until the last 15 minutes where the laws of physics got them to a place.
Oh no.
Oh, is Andy?
He's being censored.
Yeah, I think Hollywood was angry with his answer. I'm sure he'll come back. If you can hear me, let me add that one specific thing, I talked with Kip Thorne about the interstellar, and it turns out when you look at the Gargantua, the black hole that was there, you'll see that they didn't get the Doppler shift right, that both sides of the black hole are equally bright. And when I talked to Kip and I pointed out and I said to him, look, one side would be Doppler boosted because it's coming towards us, and one would be going away from us and be fainter. He said, yes, I know. Apparently Christopher Nolan just vetoed that. He was the director for that movie. So.
Are you back on, Andy?
Yeah, I'm on, I
Okay.
think. I
There's
hear myself.
Lloyd Mitchell wants to know, how is the direction of the photon ring spin produced? Is it linked to the spin of the black hole? He's asking about the direction of the spin and its relationship to the spin of the black hole.
So I think in the animations I was showing, when you spin up the black hole, the thing is sliding to the right and flattening on the left-hand side. So that's with respect to a black hole that's pointed up when projected onto the sky. So if you rotate the spin vector of the black hole, right, it's rotating about some axis, that determines which direction things are going to slide and which directions they're getting squished and so forth. So yeah, the spin arrow of the black hole determines all of these effects will be relative to that. I'm not sure if that answers the question.
Maybe he's asking fundamentally why it would spin one way or the other.
Yeah, so that just depends how the black hole was made, right? It's created out of material. Some things falling into it will carry angular momentum as they do, and the black hole will gain that angular momentum. So you can spin it up by feeding in material that's moving in one direction. You can spin it back down by feeding in material moving the opposite direction. And it just depends on the whole history of the black hole as to exactly why it's rotating in the way it is.
So there's a comment here by Carrie Liss, who's an astronomer. And I don't know if you guys know him. He's a PSW member. And if you can read his comment, maybe you can sort of summarize it and answer. Or if you like, I'll read it out loud. Hello.
I don't. Well, I don't. It's a very wonderful comment. We often think about what it would be like if Einstein were on the Event Horizon Telescope team. You know, I like to think that he just would have been tickled to death. You know, that he just would have been all hair askew and eager to go to the telescopes and start working on the data with us.
You know, Henry would have been.
Yeah. And very much so. And I really don't know. I think that he probably would have come around. Maybe Andy's better to talk to this point than I am, but I think he would have seen the evidence. He would have been convinced, as just about everybody is now. And I think he would have jumped in and started to compute, as they say. And but certainly he did reject these black holes and did not accept them, you know, even when he died.
So I'll read his comment. Carrie says, I found it fascinating to hear about Einstein's 1939 paper concerning black holes and to consider what he wrote about rejecting the idea of a cosmological constant as well. His genius was to take current physical measurements and use them to guide the next generation of theory about our universe. In his lifetime, it took the Eddington observations to verify the basic predictions of the model.
Predictions.
Predictions.
I wonder what he could have done with the measurements made by the EHT. So we'll never know.
I think Andy's doing it.
Although a lot of what, well, never mind. Andy Ludlow asks, you've mentioned the benefits that have come with increasing data rates and also looked ahead to the future benefits of more observatories on Earth or in space. Could you comment on other potential improvements to the VLBI technique, such as enhanced timekeeping or more sensitive detectors? And I think you probably know Andy is works on extremely precise measurements of time.
That's for Shep then.
Oh, I was gonna say you should do that one. I'll start. It's a great question. We're always looking to increase the precision of our instrumentation. So right now we use atomic clocks called hydrogen masers to very accurately time tag the radio waves that we see coming from the black hole. If we were to go higher in frequency, let's say 300 gigahertz, 400 gigahertz, 500 gigahertz, which would give us much higher angular resolution because of the lambda over d equation, then we would need more accurate clocks, because the clocks we use right now, even though they're very good, are not good enough to maintain phase coherence at those high frequencies. So that's one thing to do. The other thing is that we're looking to increase the supercomputers, the capacity of the supercomputers we use to correlate the data. And we are looking to go to the cloud now, where there is almost limitless computing power that can flexibly be arranged whenever we do our observing. And then Michael, maybe you want to say something about multi-frequency synthesis, which I think is really cool.
Yeah, so if we're able to observe with multiple frequencies at the same time, that's like having different baseline lengths. It's like stretching the distance between our telescopes or shrinking them. It lets us do all sorts of interesting science with that. So it's interesting that you mentioned the receivers or the detectors, because that's an area where I think detectors aren't optimized on the Earth, because we're dominated by just thermal emission from the atmosphere. There's no reason to make them more sensitive when we go to higher frequencies. But if we put something in space, there's a chance for 100-fold improvements in sensitivity if we push to really high frequencies. So I think these are the sorts of things where, I like to think, when you read these papers about black hole images, everyone always writes, this is impossible. We're just doing this for fun. So I like to think about, 50 years from now, what are they going to look back and say, we totally missed the mark and should have been more ambitious. And I think this detector technology and pushing so that we're observing over extremely wide frequency ranges is just going to open up all sorts of possibilities that we're not even thinking about today, because it seems so extraordinary.
So just do a few more questions. There was a question by David Rabinowitz that I think you partially answered here, and that was basically, what would be the benefits of moving this sort of observational study into space? He was asking about wavelengths, basically, and getting above the atmosphere, and how that would help with this sort of observation.
Yeah, well, if you want 10 times better resolution, from the diffraction limit that Shep showed, you can either you can space out your telescopes 10 times as far, or you can observe at 10 times higher frequency. But we can't observe at 10 times higher frequency from the surface of the Earth, because the atmosphere becomes opaque. So going to space, we can do anything we want. And it's just about this detector technology and seeing if we can launch instruments that have large enough apertures that they're sensitive enough to make these measurements. So both, it opens up all these new wavelengths to observe with. It also changes the types of limitations that we need for clocks, for instance. So it's, I would say it doesn't really open up that many opportunities in terms of the types of observations we're mounting today. But if technology continues to accelerate, we could be observing in completely different ways with again, resolution that could be 10 or 100 times better than what we have today.
Mm-hmm. It's really, I agree completely with Michael. It's you've got to dream, and you have to dream big. And when you think about putting a telescope in space and broadening the bandwidth, then you've got to figure out how to get the data back. So there's a huge telemetry problem. Right now we can do maybe 100 gigabits per second from space using lasers, but we'd have to go to terabits per second in order to get to all the data back from distant space-based telescopes. So there's all this really rich research and development to be done in order to make these new observations possible. And it reminds me of where we were 10 years ago. People said, oh, this is very hard, you know, it's going to be impossible. And we did it anyway. And just once you get going and you jump off cliffs and invent parachutes, then it just becomes like a way of life. So you know, once you've had one lucky streak, you want to have another one.
A question from YouTube live chat submitted by John Wetmore. Can you, what you do, we used image the sources of gravity waves. Can you use something like this approach to image gravity waves? Well, I think it's a pretty straightforward answer probably, but.
Andy?
Seems really hard because they aren't there forever. So, yeah.
Yeah, I think that's exactly right. The wonderful thing about LIGO is that they saw merging black holes, and that's what gives rise to gravitational waves. But the horrible thing about LIGO is that then they're gone, right? You can never see gravity waves from that system again. So there are two different regimes. LIGO looks at transient events, and it's hoping to find a population of those events so that it can study generally things about gravity and the precursors. And we have one or two sources that we can look at all the time. So there's a difference in the approach between the EHT and LIGO, and also, as I think Michael pointed out, the stellar mass black holes are too small. So the kind of black holes that LIGO currently sees, we couldn't see. Now, there are space-based laser interferometers that are supposed to detect gravitational waves from supermassive black holes, and those will be launched in 10 or 20 years from now. At that point, there'll be an intersection where the kind of black holes that we're looking at would also be observable with gravitational wave detectors.
So I'm going to take one last question, and this one's from Carrie. And he wants to know, or he says, black holes can have mass, angular momentum, and charge. And he asks if that's correct. And then assuming that's correct, he says, Kerr black holes assume the first two, which is mass and angular momentum. And his question is, can you ignore charge safely? I think that's one for Andy.
Yeah, there is something called the Kerr-Newman solution black hole, which has three parameters: the mass, the charge, and the angular momentum. And they're interesting for theorists like myself to study their properties. But astrophysically, the moment you have any charge on a black hole, it will, if it had positive charge, it will preferentially absorb electrons, and negative charge, it would absorb positive ions, and they would be expected to neutralize themselves pretty quickly. So that's really a question for the astrophysicists why that should happen, but that's my understanding. You expect them to not be astrophysically relevant.
You want to add anything, Shep or Mike? Oh.
Yeah, you can do these calculations, and they'll pair produce in the vacuum near the horizon, and yeah, any charge would be eliminated almost instantly. So there have been calculations on the limits here. I don't remember the exact number, but yeah, for all practical purposes, astrophysical black holes are expected to be uncharged.
The only thing I add there is that I just think it's wonderful that the three of us are on this program together. Black holes really attract everything, and I just feel so fortunate to have been attracted into the orbit of both Andy and Michael and others in this project. It's just a ton of fun. So black holes maybe even, yeah. So maybe black holes also have a fourth thing, which is camaraderie, charge, spin, mass, and beers after work.
I'll second that. Or third or fourth or fifth. Well, thank you all very much. Let's have a round of applause wherever you are to thank our speakers for coming here tonight and spending so much time with us and imparting so much interesting information about black holes, sharing their expertise and their camaraderie.
Thank you, Larry, and thank you to the hosts and sponsors.
Thank you.
We will be
Thank you.
sending you a copy of volume 1 of the PSW bulletin covering the period from March 1871 to June 1874 and telling you why the organization was founded. And you can ponder how it is that we might be actually pursuing the goals that Henry and his co-founders set out, and maybe doing a little bit of a good job with that.
You're here.
Thank you all, and you're free now. You can go and enjoy the social hour a little earlier than everyone else. I'm going to make some closing remarks, and then the program will end. But you guys are free to go.
Thank you.
Thank you so much.
Thank you.
Thank you. So before we adjourn to the social hour, we have a few closing items. PSW depends on members and sponsors to cover expenses and on volunteers to carry out its activities. There are no paid staff. If you're a member and you haven't paid your dues, please pay. If you have paid, please consider an additional donation and think about becoming a lecture sponsor. And if you're not a member, please join. You can apply for membership as well as make contributions on the PSW website, www.pswscience.org. The main requirements for membership are a genuine interest in science and a willingness to abide by the society's rules and to respect and enjoy its traditions. All PSW members are entitled to participate as attendees in all PSW Zoom webinars. Everyone is invited to view the meetings live on YouTube and to view the recordings of past lectures on the PSW Science YouTube channel. All members in good standing also may wear the PSW rosette. Members may purchase rosettes through the PSW website. PSW is a 501c3 nonprofit organization, tax exempt to the extent permitted by law and the IRS. The rest of the spring series is 2 lectures. The 2,422nd lecture will be on 5 June. It will be presented by Rajesh Rao, who is a professor at the University of Washington in Seattle. He'll be speaking on the subject when AI joins the human brain, which is basically making direct brain-computer interfaces. He has confirmed that he'll do this lecture by Zoom, so that meeting is definite. The last lecture of the spring will be the 2,423rd meeting on Friday, June 26th. We hope the speaker will be Henrik Christensen. He is professor of engineering at the Jacobs School of Engineering at the University of California, San Diego. He will be speaking on contextual robotics, and I expect to firm up in the next few days that he's going to do this lecture by Zoom. So please join me in thanking the folks who crewed tonight's lecture. James Heelan, who read the minutes, Robin Taylor, who's in the background and served as our Zoom director, and Ann McQueen, who took care of the YouTube chat questions. I have 2 final closing announcements to make. One is congratulations to PSW Corresponding Secretary Robin Taylor on defending her dissertation and completing her PhD. She is now Dr. Taylor. As many of you know, she is also an attorney and a certified public accountant, so don't mess with her. And finally, happy birthday, Connor. I hope you're online listening. Our general committee member, Connor Nixon's birthday is today. We were supposed to have a party tomorrow to celebrate, but unfortunately, that won't be possible to do in person. So happy birthday anyway. And I hope you enjoy yourself tomorrow. And with that in mind, I will now adjourn the 2421st meeting and the 89th Joseph Henry Lecture. Make your own social hour and enjoy yourselves. And thank you for tuning in